Hello. Yeah, so I guess we'll get started. So today we have two speakers. The first speaker is Gabriela. She's a postdoc research scientist in the Department of Earth and Environmental Science, also part of LEAP. He has a PhD in environmental science with a background in computer science, and his research focus is on evaluation metrics and also assessing similarities among Earth system models. And I'll let him speak more about that. So take it away.
So, Joe, thank you very much for the introduction. So, my name is Gabriela Carino, and I am a postdoctoral research scientist at Columbia University and the LEAP Science and Technology Center. And I am also a scientific affiliate at the Euro-Mediterranean Center on Climate Change, the CMCC Foundation in Italy. So, today my talk is entitled New Similarity Metrics for Earth System Model Evaluation, a multi-scale wavelet-based approach. Before I start, I would like to acknowledge this amazing team and in particular Viviana, Sarah, and Duncan for their precious supervision during my postdoc. So today we will talk about different topics. So we'll start with the limitations of traditional error metrics. We will present the set of candidate metrics for Earth system model evaluation together with the benchmark dataset, the controlled perturbations, and the evaluation pipeline we use to test the sensitivity of these metrics to such perturbations. And I also present the background on wavelet transform and how these wavelets can be applied to Earth system model maps. And we will also dive into the design of a wavelet-based similarity metric. So, as you probably know, Earth system models allow to simulate complex physical interactions within the Earth system, including atmosphere, oceans, land, and cryosphere. And this simulation generates a vast amount of multidimensional data that capture diverse physical fields across multiple spatial and temporal scales. So the assessment of differences among Earth system models output or between output and data can be reframed as the task of evaluating and quantifying similarities between these maps, right? And here I reported just a representation of all the dimension of analysis involved, because we have many different Earth system models worldwide, and each one producing a lot of variables such as temperature, precipitation, and so on and so forth across different scenarios and realizations. But these variables came with different spatial and temporal resolutions. So the problem of assessing differences is itself a complex task. And unfortunately, traditional error metrics, such as the root mean square error and similar point-wise error measures, fail to capture spatial structures and multiscale variability, which are crucial in climate and geospatial data evaluation. And here, I just reported an example of that, in which you see on the left panel an Earth system model simulation coming from the CSM2 model in December 2014, and the near surface air temperature is reported there. And starting from this reference map, we considered a couple of perturbations by adding Gaussian noise and by adding also a constant value to all the grid points of the map. And if you try to compute the root mean square error or similar pointwise metric, you get the same number, even though these two maps look very different from a perceptual standpoint. So we can conclude that the root mean square error is not a good proxy of perceptual similarity. But how do we do better than root mean square error? So we need the metrics that are not only sensitive to perceptual similarities, but also to larger scale bias, spatial structures, and multi-scale variability, but they should be also ready to analyze climate data and also tunable for specific needs. And actually, we found metrics from the image processing domain that look promising in assessing perceptual similarities. And here we reported just two relevant metrics, such as the structural similarity index measure, the SSIM, and the HAR perceptual similarity index, the RPSI. And what we did, we implemented these metrics and adapted them to handle floating point data, which are typical of climate data. thus extending their utility beyond the grayscale or RGB images. So now I would like to just give you the overview about the SSIM metric. So the SSIM basically provides a measure of the perceptual similarity between two images, X and Y. And how you do that? So basically, you can take into account three components that are multiplied together. So the luminance components that account for the brightness, the contrast, and the structure. And you can simply multiply these components together. And these components came with some weights you can tune to give more emphasis or more importance to a component with respect to the others. And the authors in the paper suggest to set these components to 1, and this gives you the explicit formulation of the SSIM that I reported below. And you see that you have to compute many statistics in the original maps, like the mean, the variance, and the covariance. And actually, the mean is a proxy of the luminance component, while the variance is a proxy of the contrast, whereas the covariance is a proxy of the structural features within the maps. And the important thing about this metric is that it is very convenient because the score stays bounded in 0, 1 when 1 indicates perfect similarity. And recently, Volksat and Carr in 2024 presented an enhanced version of the SSIM called Data SSIM for dealing with floating point data that are typical of climate and geospatial data. The other metric we considered is the Haar Perceptual Similarity Index, which measures the similarity between two images using the Haar wavelet coefficients. So the Haar wavelet is just a specific type of wavelet. And here the idea is to take these two maps, X and Y. You decompose the maps through wavelet transform across different levels on different scales. And then you basically apply the SSIM approach across different scales. And in the end, you can write or express the RPSI as a weighted combination of structural similarity index measures coming at different scales. And this allows you to capture structural distortions and perceptual differences at multiple scales. So now we introduce the set of candidate metrics, just two relevant metrics we used, but now we need to build a benchmark data set to challenge this metric, right? And that's exactly what we did. So we built a benchmark data set and an evaluation pipeline to test the sensitivity of such metrics to control the perturbations. And our database consists of air system models maps coming from CMIP6, where each static map is considered the reference map in the evaluation process. And our pipeline generates well-known perturbations of the reference map to systematically challenge the metrics. And here the goal is to analyze how metrics behave under different perturbations and to gain insight into their strengths and limitations. And below you see a picture representing the overall workflow, and in which each graphical element is an entity in our workflow. And we start from by gathering data from LIP Pangeo, and we retrieve different air system model simulations, realization scenarios, and different fields, of course. And we ingest this data in the benchmark data set, and then the evaluation pipeline starts with the set of controlled perturbation, the set of candidate metrics, and in the end we get some scores, and we use the scores to build intuitions and gain insights about how these metrics behave in different conditions, right? And here I reported an example of that in which you see the reference image and a set of spatial perturbations, including the constant offset, Gaussian and salt and pepper noise, spatial upscaling, and clockwise and counterclockwise rotations. And I refer to spatial perturbation here because they affect the field spatially, right? But beyond spatial perturbation, we are also interested in temporal perturbation. And that's why we gathered also daily data from SIMIP6. And starting from a specific day, which is our reference, we also gathered the consecutive days, and we applied them, the matrix to those maps, to get insights and intuition about how these metrics behave temporally. So now, earlier we talked about the RPSI, which is one candidate metric which takes advantage of wavelet transform to decompose the information across multiple scales, right? And now I would like to just give you the intuition about how wavelet transform works in practice. It's just a very, very easy example. So suppose you have a one-dimensional signal that we can improperly call image with a resolution of 4 pixels, 8, 4, 1, and 3. And you can basically represent this information using wavelet transform in a specific wavelet transform, which is called R. And the process is very simple, actually, because you can start by averaging pixel together and pairwise to get the new lower resolution image, okay? So you take the average between 8 and 4 and the average between 1 and 3, very simple. And you get 6 and 2. Now, notice that the original information was 4 pixel worth, but now we just have 2 pixels, right? So in this averaging and downsampling process, some information has been lost. And to recover the original 4 pixel image, we need to store some additional information that we call details coefficients. And the process is very simple, actually, because instead of taking average, you take differences and divide by 2. So you take the difference between 8 and 4 divided by 2, and the difference between 1 and 3 and divided by 2. So you get basically 2 and minus 1, which represent our details coefficients. And of course, you can repeat this process again and again on the information containing averages or approximation coefficients. And you can do that across different levels of the decomposition. And at each level, the resolution of the image halves. And in the end, you get just 1 pixel representing the overall average, followed by details coefficients at each scale, right? So in the end, you can express the wavelet transform of the original 4 pixel image as the single coefficient representing the overall average, followed by details coefficients in order of increasing resolution. But now, the important thing is that no information has been gained or lost by this process. So you can always reconstruct the original information by reversing this process. So in practice, by adding and subtracting the details coefficients from the lower resolution versions. Of course, you can apply wavelet transform also to two-dimensional maps. And here I just reported an example, and you see on the left side the reference image. And you can represent this image in terms of wavelet coefficients by simply applying these two operations, so the average and the difference. But you have to do that across the rows first, and then across the columns of the transformed maps. And in the end, you get 4 matrices, one representing the approximation obtained through by averaging, and 3 matrices containing the detailed coefficients obtained by differentiating, okay? And of course, this is just a one-level, two-dimensional wavelet decomposition applied on an air system model map. And in principle, you can iterate this process to get a full decomposition across many, many levels by acting on the approximation, on the matrix containing the approximation. You can start from this and repeat this process to decompose further, right? And this is just an example of that, in which you see the reference map here on the left side, and on the right side, you see the 3-level, two-dimensional wavelet decomposition. And the important thing here is that at each level, you see the 3 details matrices or matrices containing the details coefficients. And in the end, you see just one small metric containing the overall averages, so the approximation coefficients. And here the arrow refers to the physical spatial resolution that are involved in this decomposition, because we start with a final resolution towards a very coarse resolution in high level of the decomposition. So now the question is, how can we design a new similarity metric based on what we learned so far? So we need something which is sensitive to large scale bias, something sensitive to spatial structures, but also multi-scale, ready to analyze climate data, tunable in the sense that we have some hyperparameters that we can tune according to specific needs, and also flexible enough to be applied to different use cases, right? And that's where WaveSim comes to the game. So now let's consider two maps from our evaluation pipeline. So we have a reference maps and perturbed version of the reference, right? And in this case, we consider the Gaussian noise perturbation, which is affecting all the map, right? And starting from this map, we can get the three-level, two-dimensional wavelet decomposition of these maps. And the important thing here is that if you compare these two decomposition, you see that the coarse scale coefficients, so the approximation, the details at coarse scale are quite the same, are almost the same. And the Gaussian noise is occurring at very fine scales. So we can take advantage of this information in building our metric. So now, starting from these matrices, you can characterize the distribution of wavelet coefficients, for example, through histograms. But here, instead of how we can characterize this information, we are more interested in how to get distances between distributions, right? So you have to, you can compute distances in many ways. But now we need something to map, to turn distances into similarities, okay? And in this process, in this mapping process, we have to ensure that high distances that correspond to far apart distributions map to weak similarity and vice versa, and the similarity score remains bounded in 0, 1. And we can suggest here a potential mapping through this negative exponential in which we use distances and convert distances into similarities. And with this formulation, we ensure all these that these requirements are met. And I also reported a numerical example here in which we have distances between distributions. You can convert distances into similarities. And then we also considered, we group similarities by level and average them. So in the end, you see 4 numbers here. These are representing the similarity for the approximation coefficients. And the 3 numbers there correspond to similarities of details coefficients for each level, right? So we also provided a weighting scheme to emphasize the similarities at specific scales. And for example, if you observe major differences occurring at finer scale, then this weighting scheme could be adopted for, weight more those scales in which you see major differences. And in the end, these weights are normalized. So our final improvement that we have learned from the SSIM is that the luminance component is also important. So we want to bring this luminance component into our similarity metric to capture mean differences in the wavelet space. And this is the formula we proposed, in which similarly to the SSIM, we use the mean as a proxy of the luminance, of the brightness of the image, right? And these mean are computed from wavelet matrices, wavelet coefficient matrix, so in the wavelet space. And then in the end, with this formulation, you ensure that the luminance stays bounded in 0, 1. And similarly to what we did for the structural component, the one based on distribution comparison, we grouped luminances by level and also use the weighting scheme also to emphasize luminances at specific levels, right? So now, in the end, we can present a WaveSim as a weighted sum of two components, the luminance component and the structural component, each one with a specific weight scheme, and you can control to give more emphasis to some scales with respect to the others. And you see also there a parameter beta that you can use to give more emphasis to one component with respect to the other, right? And now WaveSim is in the matrix board, and we are still analyzing the result to see how WaveSim behaves with respect to the other metrics. And but yeah, we are very happy about that. And now next steps, and I'm going to conclude. So we foresee to improve WaveSim further by, for example, refining the weighting scheme and continue to build our intuitions about the WaveSim behavior compared to metrics from the state of the art. And we also plan to develop a validation framework since no ground truth of similarity exists. And we plan to collaborate with domain experts to construct a validation dataset and to identify metrics that best correlate with these ground truths. And also, the ground truth can help us in tuning WaveSim hyperparameters. So the weighting scheme, for example, also the parameter beta. And we will also plan to explore wavelet-based for dimensionality reduction because wavelets have been largely used for image compression, right? So in principle, we can also find a way to compare maps in a lower dimensional space. So that's all. Thank you very much. And you can reach me out in different ways by mail, on Leap, and also on LinkedIn. Okay, thank you very much.
Yeah. Yeah, a great talk. It's really cool to see this happening. My question is, if I was using this and I found, like, how do I connect this to sort of my physical understanding of, I mean, the way I think a lot of model validation does happen is something like an RMSE or people looking at things by eye or something like that. How do you connect this to kind of physical understanding? Or like, for example, like often we say, look, okay, the model isn't quite perfect because the Gulf Stream is in the wrong place. And we know that from the coarse resolution of that model, it's not going to put the Gulf Stream in the right place, but the relative SSTs around the Gulf Stream look all right, right? So it might not do so great here, but I might think it does okay. Like, see what I'm saying? Like, how do you connect those pieces? And yeah, so I wonder what you think about that.
Yeah, yeah. Thank you for the question. So it's very important actually. So so when we designed the WaveSim, we plan to use WaveSim in different use cases, right? So actually, we have to understand how WaveSim behaves in different conditions, in different situations. So it's what you were mentioning, for example, the Gulf Stream, the position of the Gulf Stream. But in principle, now we have a way to be sensitive to something which is I will say beyond what RMSE is sensitive to, because with traditional error metrics, you are sensitive to magnitude of pixel, and you don't take into account, spatial information around the pixel. Okay, right, around pixels. But now, in principle, we have this, a structural component that allow you to capture structures, and and in the set of our perturbations, we also consider the rotation, right? So if you if you have like a structure which is not located when where you expect, right? Maybe you can use the WaveSim of this metric and in particular give more emphasis to that component to see how what is the final score, and if the score is in agreement with your intuition, and okay, right? So
That makes sense, because I can imagine the process one might do is, if I have the data that I'd like my model to look like, you add perturbations or rotation to that, and then you gain an understanding
yeah,
of what that kind of is telling you. And then you could apply it to your suite of Earth system models and sort of learn. I mean, I think because basically one of the reasons people use RMSE because they feel comfortable with it, right? And they kind of have an idea of what it means, even if
yeah,
they don't
but
exactly. But like, we need to gain an understanding sort of what this actually is telling us. So yeah, great, thanks.
yeah,
Yeah.
thank you.
This is Dave. Can you hear me?
Yeah, correctly. Hi, Dave.
Yeah. Yeah, so thanks. Yeah, so I kind of have a similar question to Galen. I'm really trying to think of the applicability. I'm wondering, maybe this is just a recommendation on your next step, is to try to really come up with a specific case study that would really enable you to detect something different in a Earth system model simulation with this wave sim that you wouldn't get from RMSE. And I can't quite imagine, maybe there's some precipitation fields that might be, you can imagine there's some large scale modes, high-low patterns that are driving it, but then there's some kind of noisy precipitation at the good scale level, which might be hard to really detect whether it's getting the large scale features right. To really help us understand how it could really be applied, because showing those examples of the noise is kind of helpful, but that's not really the way the model simulation looks, right? It's not just a random noise. It's got some sort of structure to the error. So
Yeah.
and maybe, so it's not really a question, but maybe you're thinking about this. And the other thing, maybe look into literature for the weather models. I think a weather prediction has used wavelets in the past to try to pull out large scales.
Yeah.
Maybe you've already come across that literature. I know I've seen reference to it in the past. And so maybe there's some hints there about how to apply this.
Thank you very much for the comment and for, thank you for the feedback, right? Thank you.
There's a question on the Zoom. Have you validated the image reconstruction, comparing the scores?
What do you mean for image reconstruction? You mean the process of reversing the wavelet decomposition for reconstructing the original image?
We can move on to another question while I wait for the
because we don't reconstruct the image, right? So we just take the two maps, we decompose the maps through dimensional wavelet transform across a specific number or a given number of levels, right? And then we get this decomposition, and now we represented the original maps in the wavelet space, and we takes advantage of wavelet coefficient to compare distribution, basically. And this gives us the structural component. So we don't need to modify anything in the wavelet space and then reconstruct it again.
But you build the intuition.
Yeah, exactly. So we use the set of perturbations to build.
So have you validated that?
Yeah, exactly.
That your results.
Okay, now.
For both components.
Yeah, exactly. So we
valid.
don't.
This is what I meant.
Okay, gotcha. So now, okay, I understand the question. So as I said before, so we don't have really a ground truth of similarity. So perhaps we can ask a domain expert to work together and to build such a ground truth, and this would be the base to compare all the metrics. But right now we are just comparing the set of candidate metrics and our wavelet similarity based metric just to to give intuition about just by looking at scores and by looking also at the spatial and temporal structures that are that occur in the maps, right?
Okay, great.
So
Thank you. We have, sorry, we have time for what? Sorry.
You are using a 3D or a 4D?
We're going to have to move on to the next question because we need to go to the next speaker, but we have time for one more. Is that a comment or a question, Galen?
Yeah, I was just going to add kind of to what Dave was saying. I was thinking about things like the double ITCZ in the Earth system models and like patterns of ENSO, right? Those might be good candidate things that people understand, have thought a lot about, might be good ones to start with, where there's a lot of spatial structure and a lot. I mean, it's not my intuition, but a lot of other people have that intuition. So I was wondering if Dave agrees that maybe the double ITCZ might be a good candidate.
Yeah,
Yeah,
something
thank
like
you.
that.
Okay, cool.
It might be
Thank you
good
very
to
much.
maybe present this at some sort of CSM event and see if you get some feedback from people.
So thank you very much.
Thank you so much, Gabriele.